Well, hello everyone. So, in this chapter, we'll go through atomic physics. So, in atomic physics, we'll talk about mainly about three topics: quantization of energy, models of atom, and quantum mechanics. So, most of it is similar to what you learned in inorganic chemistry. Inorganic chemistry 1. So, but we'll brush up more of the physics behind the topics. So, let's go on to the first topic: quantization of energy. So before we go into the quantization, let's discuss the topic of blackbody radiation. So blackbody radiation is basically a hollow object with a small opening that looks like something like this, as shown in this figure. So light enters on one side. The light that enters never leaves. So light entering this object through the small opening strikes the interior wall. So the energy is continuously being absorbed. And this absorption of energy and after many reflections, essentially all of the incoming energy is absorbed by the cavity wall. So a black body is a perfect radiator and a perfect absorber. So a black body emits radiation based only on its temperature. So focus on this part, temperature. So a black body relies on temperature to produce radiation. So black body relies on temperature to produce radiation. So a general black body radiation. So the first example of this would be the ultraviolet catastrophe. So the ultraviolet catastrophe is the failed prediction of classical physics. So it says that the energy radiated by a black body at extremely short wavelengths is extremely large, and the total energy radiated is infinite. So this was originally proved wrong by a German physicist, Max Planck. So that's where you get the Max Planck's law of radiation. So Max Planck developed a formula for calculating the blackbody radiation in complete agreement with the experimental data at all wavelengths by assuming that one and only one principle, that energy that comes in discrete units is always quantized. So the common sense says that if you consider sand is built up of individual particles. So the idea behind light is it's a series of energy particles. So we call them quanta. So that was the idea proposed by Max Planck. So after Max Planck proposed the idea, so he tested it with the importance of understanding how it would affect the graph, the experimental data. And what he found is that as the temperature increased, the graph became more and more steeper, and it was much more easy to predict how close the values were with respect to the classical theory and then the Planck's theory. So in a classical theory, we end up with infinite chances of getting infinite wavelengths. But in Planck's theory, he says that these are fixed and they come in discrete quantities. Now, the idea behind quantum energy systems, or quanta, comes from Einstein. So Einstein applied this concept from Max Planck to light. So he understood that the light energy, the units of it is quanta, and this was the initial naming. So now we call this quanta photons. Photons are the units of light energy. So these energies are generally either absorbed, or given off as a result of electrons jumping from one quantum state to another quantum state. So the main principle behind Einstein's proposal was that light is produced due to the displacement of electrons. So the idea from Einstein was that light is either absorbed or released due to particles jumping from one state, one quantum state, to another. Similar example for this, the quantum states are basically energy states or orbits. So when electrons jump from one orbit to another, so it releases in either quantum absorption or quantum release. So either the light is absorbed or it is released. So under what conditions is it absorbed and what conditions is it released? So light is absorbed when an electron wants to go from a lower energy state to a higher energy state. So light is released when the electron tries to go from a higher energy state to a lower energy state. So this is the main principle in understanding how light systems or how light is produced. So in chemistry, we call the light as radiation. So you can use these names synonymously because they mean the same. So this was the initial idea. So then Max Planck proposed the Planck's law of radiation. So where he said that the energy of a photon is proportional to the frequency of that wave. So energy of radiation is proportional to the frequency at which it's being produced. So this, if applied, becomes equal to hf if you remove the proportionality, where h is called as the Planck's constant. So this Planck's constant is a value constant. So h is 6.626 into 10 power negative 34 joule second. So this is the value of this Planck's constant. Now, so what did Planck's constant reveal? So it revealed that this energy is proportional to the frequency. So if the light has a higher frequency, it releases higher energy. Now the common units for energy is joule, but when we talk about atomic units, we use the unit electron volt. So an electron volt is basically defined as the energy that an electron or proton gains when it is accelerated through a potential difference of 1 volt. So this energy is 1 electron into 1 volt, so which is 1.602 into 10 power negative 19 joule. So this is the common unit used to calculate the energies when you talk about atomic units. So when we talk in atomic units. Now what is the energy of a photon? So energy of a photon depends on its frequency. So a photon with a higher frequency has higher energy. So what does that mean? As you go in the spectrum towards, so gamma rays have the highest amount of energy. The next after gamma rays, you have X rays, which are a little lower than gamma rays. And after X rays, you have UV rays, which are a little lower. So as you go across the electromagnetic spectrum, the energy of the wave starts decreasing. So leading to the radio waves having the lowest amount of energy because they have the lowest amount of frequency that's involved. So using this property from Planck's law, Einstein proposed his famous photoelectric effect, so which got him the Nobel Prize for physics. So what is the photoelectric effect? So photoelectric effect basically says that the emission of electrons from a material surface occurs when the light of a certain frequency shines on the surface of the material. So the idea behind the topic was that if this is a surface, if there is a light that comes in and hits its metallic surface, and if this has an energy of hf, so then that releases electrons from that surface. So the idea behind this explained two things. One, it explained the particle nature of light. But it also explained the energy of radiation. So until the photoelectric effect was proposed, the idea was the light was a wave and it always reflects off of a surface. But after the photoelectric effect, so we started realizing the power of light. This led to the development of most of the advanced systems that we now know of. One of those is lasers. So laser systems still use the same principle of photoelectric effect. So where light energy can also be used to destroy a surface or eject electrons off of a surface. So that is the photoelectric effect. But the idea behind the photoelectric effect initially was it cannot be used for every light. So it's not possible for every light. But light for a particular frequency. For light at a particular frequency. So this principle of light at a particular frequency gave the condition to determine what frequency is it required for a light wave to eject electrons off of a surface. So this assumption we could not be explained by classical physics. To explain this entirely, so we had to create the sense of what we now know as modern physics. So Einstein assumed that an electromagnetic wave can be viewed as a stream of particles called photons. So the photon theory accounts for the observations of the photoelectric effect. So what was the idea behind this? So in terms of the photoelectric effect, what was wrong and what was right in terms of classical and experimental evidence? So in classical evidence, we assume that electrons are ejected. It depends on the intensity of the light. So that was proved wrong, and experimentally it was proved that it was dependent on the frequency of the light. The next one, the kinetic energy of the ejected electrons depend on the intensity of the light. This was also proved wrong, and it was proved that it depends on the frequency of light. And at low intensities, electrons ejection takes time. This was also proved wrong. It said that it occurs almost instantaneously above a certain frequency. So the main idea was from the system of frequency, energy systems of frequency. So at a particular frequency, we start seeing ejection of electrons. Now this idea gave rise to a frequency value. So that frequency value is called the threshold frequency. So the name threshold means it's the minimum frequency required for the ejection of electrons. So no electrons are emitted if the frequency of the incoming light falls below a certain frequency. So that frequency is the threshold frequency or the minimum frequency. So the smallest amount of energy the electron must have to escape the surface is called as the work function of the metal. So the work function of the metal is written as WF and it is written as HFT. So where FT is the threshold frequency and WF is the work function. So work function can be described as the minimum work required before a metal starts ejecting electrons off of its surface. So this is the work function. So we write WF is equal to H into FT. So because the work depends on the frequency, so for any ejection of electrons to occur, so it has to reach a specific threshold frequency, only after which it starts ejecting electrons. So this is the initial idea for the work function of a metal. Now, so the photoelectric effect also gave rise to the understanding of the same conservation of energy. So we know that energy should be conserved, which means that the maximum kinetic energy of the photoelectrons ejected from the surface is the difference between the photon energy and the work function. So we can consider that the kinetic energy difference, delta kinetic energy, is the difference in the energy minus the work function, HF. So this value is what we call the maximum kinetic energy of the photoelectron. So maximum kinetic energy. This kinetic energy is the energy of the ejected electrons. So because these electrons are ejected by light, so we call these electrons photoelectrons. So we call them photoelectrons. So another principle that can explain how the particles move is the process of quantum shift. So we understood that from the photoelectric effect, so light behaves like a particle. So then photons should have some momentum. So because the understanding a particle should have a momentum, because a particle is considered to have mass. Now, the idea behind this was if it has maximum momentum, then both the quantities should be conserved in elastic collisions. So the American physicist Arthur Compton, so he used X-rays and towards a block of graphite to test this theory. So what he found was that scattered waves had less energy and longer wavelengths than the incoming waves had just as he had predicted. This change in wavelength, what is defined as the Compton shift. So it still is the same as that of any other system. So if you take a light wave, the light wave has a certain momentum and the electron has a certain momentum. For example, if you consider P1i and P2i, after the energy systems evaluation, so the electron starts moving and the light wave starts slowing down. So we can write it as P1i and this becomes P2f. So we can still understand that P1i plus P2i is equal to P1f plus P2f. So this was the initial idea of quantum shift. So what he found was that both the waves generally try to mix together and make sure that they do undergo elastic collisions. They still undergo elastic collisions. So that ends the process of quantization of energy. So in the next section, let's discuss the models of the atom. So the first early models were first proposed by J.J. Thomson. So J.J. Thomson he predicted that the electrons are embedded in a spherical volume of positive charge. So he understood that. So the other name for this model, was the watermelon model. So it does not hold true when the next experiment was proposed. So the next experiment was done by Ernest Rutherford. So Ernest Rutherford wanted to check if J.J. Thomson was right. So from this came the famous gold foil experiment. So he took a small gold foil and put a detector on outside of it. So this is the gold foil. And he fired from a source, alpha particles. Alpha particles are basically helium particles, 2-4 particles. So he fired them across the gold metal. So if the idea was that if JJ was correct, then the alpha particles would be all over the place and never pass through the foil. So what he found that JJ was not correct. So he found that there are rays that used to go straight through, and there were rays that were completely reflecting back to the source. So this gave the idea to Rutherford, where he proposed the famous Rutherfords Model. So using the experimental results that he had, he proposed a hypothesis saying that the positive charge is not spread out but concentrated. Number 2, positive charge was stronger and smaller than the negative charge. So these were the two things that he proposed. So all of the positive charge is in the atom. Most of the atom's mass is found in a region that is small compared to the size of the atom. So he called this region the nucleus of the atom, and any electrons in the atom were assumed to be in the relatively large volume outside the nucleus. So this was the first case of understanding the earliest model of an atom. So this was the first step in understanding the earliest model of an atom. So he proposed that electrons were not being pulled into the nucleus, because electrons they are moving around the orbit as an orbit around the nucleus. So these accelerated charges, they are radiating electromagnetic waves and losing energy. So this will lead to a rapid collapse of the atom. So this difficulty led scientists to continue searching for a new model of the atom. So Rutherford's model could not explain how electrons were able to revolve without collapsing. So this was the first backlog for the earliest model of the atom. So then came the topic of atomic spectra. So proposed by Niels Bohr. So what he said is that when light is passed through an atomic gas, it splits. So it passes by through any prism. So he proposed that there are a series of distinct bright lines are seen. So each line corresponds to a different wavelength or color. So this diagram is called as the emission spectrum, and every element has a different emission spectrum. So the idea behind Niels Bohr was that each material passes a certain frequency of light. So this gave rise to the topic of atomic spectra. So an element can absorb light at specific wavelengths. So the spectral lines correspond to this process are called as the absorption spectrum. So in an absorption spectrum, the light of all wavelengths pass through a vapor of element being analyzed. And in the absorption spectrum of a given element, it coincides with the emission spectrum of that element. So wherever the emission spectrum showed a certain value, that was missing in the absorption spectrum. So if you keep them right next to each other, so they fit in like puzzle pieces. So noting down the light that they can emit and light that they can absorb. But this became the question, how can materials absorb and emit light? So this was first proposed only for hydrogen. So it is called as the Bohrs Model of the hydrogen atom. So what did Bohrs Model say? So the first thing was that in Bohrs Model, there were only certain orbits that are allowed. The electron is never found between these orbits. So instead, it's said to jump instantly from one orbit to the other. So in Bohr's model, there are transitions between the stable orbits with different energy levels. So that account for the discrete spectral lines. So the discrete spectral lines refer to the separation in the spectral lines in each of these cases. So what does the Bohr's model say? So the Bohr's model basically says that when a light of continuous spectrum shines on the atom, so the photon energy matches, if the energy matches with the energy separation between the two levels, it will be absorbed by the atom. Then the electron jumps from a lower to a higher energy state, which corresponds to an orbit farther from the nucleus. So when it absorbs light, it passes from a lower energy state to a higher energy state, provided the light corresponds to the energy level. The light corresponds to the energy level. So for example, if this is an energy level and this is the other energy level, so the lowest energy level is called the ground state. Anything above the lower energy level is called as the excited state. So if you have an electron, if the electron absorbs light, it goes from a lower energy state to a ground state to an excited state. So here there is absorption of energy, absorption of light. And when this electron comes back to the ground state, it releases energy in the form of HF, radiation. So this is a release of or emission. So this results in emission of light. So this was the primary idea proposed by Niels Bohr. So this, when you have the Bohr's model, so Bohr's model proposed that there are what we call quantum energy levels. So the energy levels are separated by their orbits. So the largest energy difference is between the ground state and the second energy level. So as the energy levels start increasing, the space between the energy levels starts decreasing. So for example, if you consider n equal to 1, just as n equal to 2, n equal to 3, n equal to 4, and this n equal to 5. So in these energy levels, each of them have its own energy. So with the ground state having the lowest amount of energy. So any electron can jump directly from orbit 5 to orbit 1. Or orbit 5 to orbit 2. So orbit 4 to orbit 1. Orbit 3 to orbit 1. Orbit 2 to orbit 1. Or they can jump directly from orbit 5 to 2, 4 to 2, 3 to 2, or they can jump from 5 to 3, 4 to 3, or 5 to 5. So each of these cases happens only with a particular frequency of light. So for it to jump from a higher energy, so any electron just from higher energy to the first orbit releases UV radiation. So this series of lights releases UV radiation. And this jumping from 5 to 4 to 5 to 2 to 4 to 2 or 3 to 2 releases visible light. And anything after that releases IR radiation. So this is the topic of quantum energy levels. So what does the Bohrs model say? So Bohrs model was not considered to be the complete picture of the structure of the atom. So it was assumed that the electrons do not radiate energy when they are in stable orbit. So but his model did not offer an explanation for this. So another problem with Bohrs model was that it could not explain why electrons always have a certain stable orbits. So these were the things. So for this, scientists continued to search for the new model of an atom. This led to the final standard model that we now use, or the other name for the standard model is the quantum model of an atom. So with Niels Bohr, Planck, Einstein, and many other physicists came the science of quantum mechanics. So quantum mechanics tried to understand the behavior of microscopic particles. So the first was the dual nature of light. So we'll continue the topic of dual nature of light. So dual nature represents the main problem with light is because light sometimes behaves as a wave, but sometimes behaves as a particle. This has been one of the mind-boggling things about light because it cannot act at the same time. It can act as both at the same time. So there is a considerable evidence for photon theory, but there is also a considerable evidence to consider that they are electromagnetic waves. So what we are understanding here is that the electron has which wave behavior or the light photon behavior. So which model is correct? So one of the first models to accept, so some of the experiments conducted better explain the model of photon. Some of them require a wave model. So most physicists generally accept both models and believe that the true nature of light is not describable in terms of a single classical picture. So at one extreme, the electromagnetic wave description suits the overall interference pattern. At the other extreme, the particle description is more suitable for dealing with high energy photons of very short wavelengths. So in reflection, so when you take the wave model, it suits reflection, it suits refraction, it suits diffraction, interference, but it does not explain the photoelectric effect. The particle model explains reflection, refraction, but it does not explain the bending of light and the superposition of light, but it can explain the photoelectric effect. So one of the first scientists or one of the first physicists to understand this was Louis de Broglie, a French physicist. So who said that light itself is a matter wave. So focus on the term matter wave. So it's a wave filled with matter, or it's a matter that acts as a wave. So whichever one you consider. So this property explained the concept of wave particle duality. So what de Broglie proposed was that he proposed that all forms of matter may have both wave and particle properties. So his first experimental confirmation was when he noticed that electrons can not only act as particles, they can undergo the same interference patterns. They can behave like a wave. So the electron diffraction was the first place where he found that particles themselves, subatomic particles, can act as both waves and particles. So he proposed that if you consider both the theories, so he used the Einstein's theory of E equal to mc square, and he used the Max Planck's theory of E equal to hf, and this represents the particle nature. This represents the wave nature. Because notice that mass refers to the particle, frequency refers to the wave. So he combined both, so that results in hf equal to mc square. So when you want to find h into, so we know that c equal to f into lambda. So from this, if we calculate f equal to c by lambda, so it becomes hc by lambda is equal to mc square. So cc gone, you get h by lambda equal to mc. So if you rearrange the values, so you get lambda equal to h by mc. So the wavelength is a property of inversely proportional to the mass. So as the mass increases, the wavelength decreases, or as the mass decreases, the wavelength increases. So this gave rise to the wavelength. So this wavelength, lambda is equal to h by mv, is called as the de Broglie wavelength. So what de Broglie proposed was that it acts as a matter, so it acts as particles, but the particles themselves propagate in waves. So what he proposed was that if you consider an orbit, so what he said was that the particles do not stay constant. So as a particle themselves, they are continuously vibrating across the wave and behaving like a wave inside the system. So this was the initial idea of de Broglie waves or matter waves. So I'll explain it again. If you consider an orbit, the particles inside the orbit are not constant, so they are also constantly moving around in the form of a wave. So these waves are called matter waves, and the wavelength of these waves is the de Broglie wavelength h by EMV. So this was the first understanding of matter waves. So we can calculate for each orbit's radius what is the wavelength. So you can consider that. So this is an integral multiple. So as the matter wave starts increasing, so you start noticing that the initial one is lambda, the second one becomes 2 lambda, the third one becomes 3 lambda. So the radius is an integral multiple of the wavelength. The radius is an integral multiple of the wavelength. So then came Heisenberg, a German physicist, who put the most confused and the most misunderstood concept of physics called the uncertainty principle. So what was the argument made by Werner Heisenberg? So he proposed that it's fundamentally impossible to make simultaneous measurements of both the particle's position and the particle's momentum with infinite accuracy. What does that mean? So best example of this would be to look at a fan. So look at a fan. And let's say if the fan has blades, right? So let's look at a fan blade. The fan starts rotating. If you keep the focus on the blade, keep the focus on each blade, then you cannot know how fast it moves. And if you notice how fast it moves, you cannot focus on the blade. So this is the idea behind Heisenberg's uncertainty principle. So his idea was that when you calculate the position, so if you know the position, you cannot know the momentum, or if you know the momentum, you cannot know the position. So to put it in words, so the uncertainty in the measurement of the position and the uncertainty in the measurement of momentum is always greater than or equal to h by 4 pi. So if one increases, the other compensates for it. So this results in delta x. And if you consider P here as mv, you can write it as h by 4 pi. So you can write delta x into delta v as mass is constant, so it becomes h by 4 pi m. So this is the law of, it's not a law, it's the principle of uncertainty. It's the principle of uncertainty. So this was the Heisenberg's uncertainty principle. So this brings us to the final concept, the electron cloud. So electron cloud was the theory proposed by Erwin Schrödinger. So Schrödinger's hypothesis was that an electron did not have a definite path, so it does not have a definite position. So it does not have a definite position in the orbit. Rather than having a definite position, so the electron's position is not deterministic, but probabilistic. So the idea behind Schrödinger's principle was that it did not have a path, but there was a certain region in space. So there was a region in space where the electron's probability is 100%. So each orbit, rather than having a single path, it was a region. That region contains the probability that you can find an electron there with 100% certainty. This was the principle explained by Schrodinger. So where he said that the electron having an orbit, it makes a cloud. So because the cloud is easy to explain the term probability, because cloud, the electron can be anywhere. So rather than knowing the electron's position, exact position, we consider that it's probabilistic and the electron can be anywhere. So this was the theory proposed by Erwin Schrodinger. So he proposed that as there is a certain distance where the probability of finding an electron is the highest, and as you go away from that distances in towards the left or right, the probability starts decreasing. So this was the concept of electron cloud. So that ends the topic.